I had this moment the other day that I think perfectly encapsulates the whole frustration with modern tech. I was actually yelling at my smart speaker.
Always a highly productive way to start the morning.
Right. But uh, here's the thing. I bought this device 2 years ago, and it felt like absolute magic. It was top of the line. It knew all the trivia. It could set 3 timers at once. But I realized yesterday, just standing in my kitchen, that this thing hasn't learned a single thing about me since the day I peeled the plastic off.
Not one thing.
No. I've changed my routines,
Well,
I've moved furniture,
look.
I've changed my diet, but the device, it's exactly the same as it was on day one. It's frozen in amber.
Yeah, that is the classic static intelligence problem. You are dealing with a device, well, really an underlying model architecture that has a massive amount of knowledge, but absolutely zero ability to grow.
Right.
It is like hiring a genius consultant who gives you amazing advice on Monday, but then outright refuses to learn a single new fact about your company for the next 5 years.
Exactly. And that exact frustration is really the launch pad for our deep dive today. We are unpacking a research paper that I honestly think is going to define the next few years of AI development.
It's a big one.
It is. It's titled Learning to Learn at Scale, Promises and Challenges, published just this month, February 2026, by a team over at the Shenzhen Institute of Artificial Intelligence and Robotics for Society.
And this is a heavy hitter for you listening. This isn't just another paper about how do we make the model bigger or how do we add more parameters. This is a paper arguing that the way we currently build AI specifically, this massive pre-training phase where we feed it the entire internet that might actually be a dead end if we want machines that can truly adapt.
Which is a massive claim. I mean, you look at the headlines and companies are spending billions on these pre-training runs. They're building data centers the size of small cities. And these authors are essentially saying, hey, you might be driving toward a cliff.
In a way, yes. They are saying we were optimizing for the wrong thing entirely. So the mission for this deep dive is to figure out why they think the current path is broken and what the alternative, this concept called learning to learn, actually looks like in practice.
Because if they are right, we are currently spending all our resources building massive libraries when we should be building students.
I love that distinction, libraries versus students. It frames the whole problem perfectly.
So let's set the stage for everyone. What exactly is the status quo right now?
Right now we have foundation models. You know them, you use them every day. And they are incredible at passing standardized tests. They write Python code, they summarize the history of the Roman Empire, they can write a sonnet about a toaster.
They're great party tricks.
Exactly. But the authors ask a very uncomfortable question here. Do these models actually know how to learn? Or are they just really, really good at retrieving data they have already seen?
It is the difference between actually understanding physics and just memorizing the answer key to the physics final.
Precisely. And the answer in the paper is a pretty hard no. They argue that once these models leave the factory, once that massive training run is done, they hit a brick wall. They get deployed and they become completely static.
They can't adapt to new environments or tasks independently.
Right. The industry is facing this huge bottleneck because we've maximized knowledge. The library is full, but we have completely neglected adaptation.
Okay, so let's unpack their solution then. The paper talks about learning to learn, or L2L, and they use this concept of a nested loop to explain how intelligence should actually work. Help us visualize that, because honestly, nested loop sounds like something that would instantly crash my Excel spreadsheet.
It does sound technical, but it's actually very intuitive if you just look at biology. Imagine your brain, or really the human species as a whole, has 2 gears.
Okay, 2 gears.
There's the slow gear, that's evolution. Over millions of years, humans evolved eyes, hands, language centers, and basic survival instincts. That is slow, permanent foundational change. The paper calls this the outer loop.
Got it. Slow, permanent foundational. So in AI terms, that is the pre-training phase.
Exactly. The pre-training updates the slow weights. It is the DNA of the model. It determines the starting point. But then there is the fast gear. Your working memory.
Like day-to-day stuff.
Right. That is you walking into a strange airport you have never been to before. You have to figure out where the gate is, navigate the massive crowd, decide to buy a coffee all in under 30 seconds. You aren't physically evolving new neurons or growing a third ear to do that. You're just adapting to the immediate context.
So that is the inner loop.
Exactly. The inner loop updates the fast weights. This is the immediate, rapid adaptation to the task right in front of you. The paper argues that true intelligence isn't just having a great outer loop, a huge library of facts. It is about how efficiently that inner loop can operate, Can you walk into a situation you've never seen and figure it out on the fly?
And their argument is that our current AI models are basically all outer loop and almost zero inner loop.
Or rather, their inner loop is deeply broken. Now, the paper does mention that for a long time, researchers actually tried to build this inner loop using something called gradient-based learners. You might see the acronym MAML thrown around in the literature. That stands for Model Agnostic Meta-Learning.
Which sounds like a very complicated sandwich.
It is a very complicated math sandwich. And the paper points out this approach was essentially a dead end when it came to scaling up.
Why is that? What went wrong with it?
Think of it this way. Gradient-based learning is essentially like doing brain surgery on yourself while you're awake. Every single time the AI wanted to learn a new task, say recognizing a completely new type of dog, it had to mathematically calculate derivatives and physically update its neural connections.
Oh, wow.
It had to rewrite its own underlying code while it was trying to do the work.
So if I am trying to learn how to play tennis, after every single forehand, I have to stop, cut open my skull, and rewire my brain cells before I can hit the next ball.
That is a very visceral image, but yes, essentially. It is computationally incredibly expensive to do that. It requires calculating second-order derivatives, which involves massive matrices of numbers. It just didn't scale.
Yeah.
You simply cannot do that in real time. But the paper points out there is a winner emerging, model-based learners.
And this connects to in-context learning, right? This is the taking notes approach versus the brain surgery approach.
Yes, perfectly said. With model-based learning, the AI is not rewriting its permanent weights. It is using its activation state, basically its short-term memory, to hold information. It is just holding the context in its mind and using that to change its behavior. It's fluid, it's fast, and it doesn't require a surgeon.
Okay, so we've moved from rewiring the brain to just using working memory. That makes total sense. But this leads to what I thought was really the most important distinction in the entire paper. I actually had to read this section twice because it totally flips the script on how we judge AI. It is the difference between in-weight learning and in-context learning.
This is the absolute crux of the argument. If you take one thing away from this deep dive today, let it be this distinction right here.
And they use this bedroom analogy to explain it, which I found incredibly helpful, but also kind of damning for current AI models.
It is extremely damning. So let's role play this a bit. Let's say you ask an AI model, what is in the bedroom?
Simple enough question.
If the model is relying on in-weight learning, that's the stuff it memorized during its massive pre-training run, it acts like a statistician. It scans its internal database of millions of bedroom photos it saw during training. It sees that, statistically speaking, 60% of American families have a TV in their bedroom. So it confidently answers, there's likely a TV.
It is just playing the odds. It is not actually looking at my bedroom. It is looking at the average bedroom. It's basically guessing based on what's popular.
Exactly. It ignores the specific reality in favor of the global average. But a model using true in-context learning acts like a detective. It looks at the specific description or the specific image you just handed it. Let's say you provided a photo where the room is completely Spartan. There's just a bed, a lamp, and a window.
The detective ignores the historical statistics. It trusts its own eyes. It says, there is no TV.
Right. And here is the scary part of the paper. The authors argue that our current method of pre-training, feeding these models petabytes of random internet data to make them smart, is often accidentally boosting the statistician and completely starving the detective.
Wait, really? Because I always just assumed that if we feed the model more data, it inherently gets smarter. You were saying it just gets more opinionated?
It gets more knowledgeable, but not necessarily more adaptive. When you have that much data, the model can often just memorize the answer to almost anything. If it has seen 1 million bedrooms, it feels like it doesn't need to look at your specific bedroom to make a decent guess. We call these emergent abilities in the industry, but the paper argues they are highly deceptive.
Because we don't know how it got the answer.
Exactly. We don't actually know if the AI is solving a problem because it's genuinely smart and using in-context learning, or just because it cheated and memorized the answer key using in-weight learning.
So we are basically building these incredibly confident trivia champions who completely fall apart the second they encounter a unique situation that isn't written in their textbook.
That is a perfect way to put it. We are masking a fundamental lack of reasoning with just an absolute abundance of memory. And nowhere is this failure more obvious and honestly more shocking than when we switch from processing text to processing vision.
Yes, part 3 of the paper. This section really surprised me because we used to tend to think, oh, AI can generate gorgeous art. It can identify a cat in a photo. It can drive a car. So vision must be solved. But the paper says vision is much, much harder for these models than text.
The numbers they provide are stark. They compared the minimal achievable loss, which is basically a score of how hard it is to accurately predict the next piece of information. Lower is easier. For text tokens, that score is about 18.3.
Okay, 18.3. Keep that number in mind.
But for vision tokens, it is 53.3.
That is a massive gap that's nearly 3 times harder. Why is looking at a picture so much harder for an AI than reading a sentence?
It comes down to what the paper calls open-ended diversity. Think about language for a second. If I say, the cat sat on the face, your brain automatically creates a very short list of possibilities. Mat, rug, floor. Maybe hat if we're reading Dr. Seuss.
Right, text is narrow.
Exactly, text is determinate. It consists of symbols pointing to specific agreed-upon concepts. But an image is a whole different story.
Because if I say, show me a graduate student's bedroom, think about the infinite possibilities there.
Right. Is it messy or clean? Is it day or night? Are there posters on the walls? Is there a half-eaten pizza box on the floor? What is the lighting like? Is the bed even made?
Texture, perspective, angle, occlusion, there's just so much happening.
An image contains an abundance of details that are simply not strictly determined by the text prompt. Because of this relying on that statistician approach, the in-weight learning fails miserably. You cannot just memorize the average look of a room because every single room is distinct in a million tiny little ways.
And they proved this failure with an experiment that honestly I laughed out loud when I read the results. It is the Object Nav experiment. Walk us through this one, because it sounds like a prank we would play on an intern.
It does feel a bit cruel, honestly. So they took a vision language model, the QuenVL27B, which is a very capable model, by the way,
Right.
and they put it in a virtual robot. The task was incredibly simple. Navigate a house and find a specific object like a bed or a sofa.
Sounds easy enough for a supposed superintelligence. Just go find the sofa.
You would think so. Now, they ran this experiment in 2 distinct modes. Mode 1 was zero shot. They just dropped the robot in the house completely blindly and said, go find the bed. It had to figure it out as it walked around.
Okay, it's blind navigation. And what was mode 2?
Mode 2 was the context mode. Before asking it to find the bed, they actually gave the robot a full room tour. They showed it a continuous video sequence of the house, giving it all the context it could possibly need to build a mental map. It essentially got to walk through the house first.
So logically speaking, the robot with the tour should absolutely crush the robot that is going it blind. It has the answers. It literally has the map.
That is what human logic dictates. But the result was the exact opposite. Providing the model with the room tour context actually resulted in worse, or at very best, equal performance compared to going in completely blind.
That is wild to me. You literally give it the answers and it somehow gets more confused. How is that even mathematically possible?
The paper states it effectively exhibited almost no ability to learn from context. It proves that these vision language models are acting as static memorizers. When the robot went in blind, it just fell back on its statistical priors. Beds are usually in bedrooms, bedrooms are usually down the hall, and it just stumbled its way there. It was guessing based on historical averages.
But when you gave it the actual video tour,
It didn't know how to process that new information at all. The detective part of its brain is so atrophied that the extra clues just became overwhelming noise. It interfered with the statistician. It is like someone who has perfectly memorized a street map of New York City, and when you drop them in Tokyo and hand them an accurate map of Tokyo, they throw it away and say, no, I'm pretty sure Fifth Avenue is this way.
it trusts its massive training data more than its own immediate eyes. That is deeply problematic if we want robots to actually do things in the real physical world. I mean, if I buy a robot butler, I need it to navigate my messy house, not the pristine average house it saw on the internet.
Precisely. And this is exactly why the authors argue that simply scaling up, just making the models bigger and feeding them more static data won't solve the core problem. If you make the library bigger, you don't magically get a better student, you just get a heavier library.
So if the current path is a dead end, or at least a major plateau, what is the new path? The paper proposes a massive shift in how we treat data and memory entirely. Let's talk about the generalization gap, because this seems like the exact business problem that is going to make this shift really hard for companies to swallow.
This is the trade-off that is currently keeping AI CEOs awake at night. The research shows that if you want to build a model that is a true learner, one that uses in-context learning effectively, you have to train it on a massive range of diverse tasks. You have to force it to struggle with variety.
Okay, so diversity makes you adaptable. That sounds good on paper. What is the catch?
The catch is that initially, if you train a model to be a generalist, its performance on specific standard benchmarks actually drop.
Oh, I see. Because the industry is completely obsessed with benchmarks.
Yeah.
Everyone wants to be able to say, our model scored 99% on the LSAT.
Exactly. And the core researcher tells the CEO, hey, I can make a model that learns way better in the long run, but it's going to score an 80% on the LSAT benchmarks this year because we are spreading its attention across 1,000 different types of obscure problems.
And the CEO says, get out of my office. I need the 99% for the press release tomorrow.
Pretty much. But the paper argues that the generalist model, despite that lower initial score, will eventually overtake the specialist because it can rapidly adapt to new unseen tasks that were never on the original test.
It's the difference between cramming for a test and actually understanding the subject material. The crammer gets an A today, but fails entirely in the real world. The learner might get a B today, but ends up running the company in 10 years.
That is the generalization gap in a nutshell. And to close that gap, the authors propose an entirely new type of data diet. We need to move away from fragmented data.
Fragmented data being what we use right now mostly.
Yeah. Random Wikipedia articles, 10-second YouTube clips, isolated snippets of code. It is all completely disjointed. It's just flashcards. There is no continuity to it. The paper proposes we shift to full lifecycle data.
Which sounds intense. What does that actually look like in practice?
Imagine recording everything a person sees, hears, and does for 20 years straight. You don't just see the final polished skill, you see the struggle, you see the toddler falling down 20 times before finally walking, you see the student getting math problems wrong, correcting them, and then finally getting them right.
So the AI gets to watch the process of learning, not just the final result of learning.
Exactly. By training on long sequences that cover an entire lifetime, the AI learns the actual underlying patterns of adaptation. It learns that, oh, when I encounter something completely new, I should look for contextual clues around me, rather than I should just quote a static statistic from my database.
It is building a narrative of growth. That's genuinely fascinating. It's almost like the Truman Show, but for AI training data. But there is one more critical piece to this puzzle, right? Memory. Because right now, AI memory is kind of rigid and messy.
Very rigid. Current systems mostly use manually designed rules for what to keep in their context window. It is like a programmer literally writing a hard rule. Always remember the last 10 sentences. But that is not how real brains work at all.
No, definitely not. I remember a weird joke a kid told me in 3rd grade, but I completely forget what I had for breakfast yesterday.
Right, because the joke was novel or it was emotionally resonant in some way. The paper calls for trainable long-term memory. The AI needs to actually learn what to forget and what to keep. It needs to manage its own brain space effectively.
It needs to build a filter.
Yes. If it tries to remember absolutely everything, it slows down. Computationally, it just becomes a swamp. But if it forgets everything, it obviously can't learn. It needs to develop its own intuition for information value. It needs to decide, this casual conversation about the weather, delete that. But this new instruction on how to open the secure door, keep that permanently. This isn't something we can just hard code. The model has to organically learn the policy of memory itself.
So to summarize where we are at today, we need to stop building static libraries, that is the pre-training obsession, and we need to start building students, that is learning to learn. We have to accept that they might look dumber at first on standardized tests, so they can't actually be smarter in the real world later. And we need to feed them life cycle data, the full movie of life, not just disconnected screenshots, so they genuinely learn how to learn.
That is a perfect summary. It is a fundamental shift from viewing intelligence as knowledge to viewing intelligence as adaptation. And frankly, it is the only viable way we get to true autonomy.
You know, it's funny. As we talk through all of this, I cannot help but feel like we are really just describing us, humans.
It is the ultimate mirror, isn't it? We don't come into the world with Wikipedia preloaded in our brains. We come in with very little in-weight knowledge. We can't do calculus at birth. But we have incredible in-context machinery. We are the ultimate detectives from day one.
And maybe that is the humbling part for the tech industry. We have been trying to brute force AI just by shoving all of human knowledge into a massive hard drive, thinking that alone would create a mind. But a mind isn't a hard drive. A mind is an active process.
It is, and the paper heavily suggests we need to respect that process. We cannot shortcut evolution by just downloading the internet. We have to build systems that can experience the real world, get confused by it, and then dynamically figure it out.
Which brings us to the big question I want to leave you with today.
Hmm.
We live in a world of absolute instant gratification. We want the AI that works perfectly right now. We want the stock price to go up right now.
But the research clearly suggests that the path to true artificial general intelligence and AI that can actually handle the chaotic open world might require us to take a deliberate step back.
Are we willing to trade immediate competence for long-term adaptability? Would you buy a dumb AI assistant today if you knew that in 5 years it would be the only one that actually truly knows you?
That is the big gamble. And right now, the entire industry is betting on the library. But if this paper is right, the smart money might actually be on the student.
Something to think about the next time your smart speaker completely refuses to understand a simple request. Thanks for diving in with us today.
Always a pleasure to be here.
Catch you on the next deep dive.